This is a big topic today, which is error in Taylor polynomials. But before we get to that, I figured we would begin with another example. We are going to compute the third order Taylor polynomial for this function centered at a equals 1. This is a nice review of what we did last time. So we make a chart. My center is 1, and then the last column, which is the column of coefficients in my polynomial, we divide by k factorial. And then we need third order. Okay, well, this is the original function. Maybe I'll write it this way, 1 plus x to the minus 1, because I'm going to start differentiating. So the first derivative is minus 1 plus x to the minus 2. I get a 2. 1 plus x to the minus 3. I have negative 6. 1 plus x to the minus 4. Okay, and that's as far as I need for third order. Okay, now I evaluate out 1. Well, inside the parentheses will be 2 for all of these. 1 plus 1, 2. So here, this is a half. This one is negative 1 over 2 squared. This one is positive 2 over 2 cubed, which is 1/4. And here, 2 to the 4th is what? 4 and 4, 16. We're going to get a negative 6 over 16, which is the same thing as, let's see, divide by 2, negative 3 over 8, like this. Okay, I could have left them unsimplified. That would have been okay too. Especially if I was going to try to write the Taylor series, which we started talking about last time, because sometimes leaving the coefficients unsimplified, you can find the pattern better. But this is a practice of third order Taylor polynomials. Now I divide by k factorial. So here 2 factorial is 2, so I get an 1/8. And then here, when I divide by 3 factorial, this is 6. Well, this would have been easier to see leaving it like this. I get a negative, I already have my negative. I get a negative 1 over 16. And so this, which we started doing last time, this T3Fx1 with this notation, this third order Taylor polynomial, well, this is a half minus 1/4 x minus the center plus 1/8 x minus the center squared, and finally minus 1/16 x minus the center cubed. Okay, so this is my third order Taylor polynomial. And for example, what can I use this for? Because this is going to move us into error. For example, well, this is kind of a silly function to do this for, because it's not that hard to evaluate this function. But if I wanted to evaluate, let's see, if I wanted to evaluate, for instance, this is centered at 1, so let's say 1 over 2.1. Well, this we know, given my function, exactly we know what it is. This equals f of, well, 1.1, right? If I want to get an approximation of this where I am just evaluating polynomials, this is approximately TF3 and then 1, which now this equals, well, I would just evaluate this thing at 1.1. This is just 0.1, okay, and then plus 1/8, 0.1 squared minus 1/16, 0.1 cubed, like this. The actual value, 1 over 2.1, which is the function value at 1.1, this I get is 0.476190. That is to 1, 2, 3, 4, 5 places. This one, which was, the difference is not polynomial. This one was polynomial evaluation. This is our Taylor polynomial. This value, 476,188 to that many decimal places. 476,18875 is what this shows me, and I will round to this to match 6 decimal places. Okay. What we see is, at least visually, we see this is a very close approximation, right? Well, what we just saw is this example here, 1 over 1 plus x. And we calculated through, let's see, T3. Okay, so let me erase T4 and T5. We calculated through the third order Taylor polynomial at center a equals 1, okay? And we calculated, so here, oh, well, I don't want to show this for a negative. I'm really focused on nearby 1, okay? And what we see here, this would be the tangent line. It is the first order partial sum. This is the best quadratic. This is the second order partial sum. And this is this third order that we computed. Of course, you can keep going with this and taking derivatives if you want. Now, then I used this so to approximate. For example, I can compute this over here on the side. I can compute, what do I call this? T sub, capital T sub 3 of, well, it was 1.1. And I showed this on the board. You see the value here. It is 0.4761875, right? Now then, here's this point, which I will now take off my center and take off the label and put this, okay? Which, again, to the first 3 decimal places, it looks exactly the same. Well, if we start zooming in, now let's see. If we start zooming in, it is on, my graph is black. So maybe I will take off T2 and T3. This is literally on the graph. And we can already see zooming in at this level where it's not exactly the tangent line. We could compute the error. Okay, but T2 and T3 is what I calculated. I'll remove the tangent line. And let's keep zooming in until we realize that this might take a few more zooms. It was very close, right? This third order approximation. Now we are starting to see, look, this blue is my Taylor polynomial, right? And I'm using it to approximate my function value. But you see, they're not the same. Of course not, because 1 over 1 plus x, which is graphed in black, is not a polynomial. Okay, so this here, the difference between the black, which is my actual function value, and here in blue, which would be down here, okay, which to 4 decimals is no different, but the approximated value by this Taylor polynomial, evaluating my Taylor polynomial at 1.1, this difference is the error. And this is what, of course, for any given function, if you can compute this, which we can here, we can just take the difference and we know the actual error. But what we want is a theoretical upper bound for this difference that we see right here in the graph, right? We see, in fact, I can probably, let's change this point to be, this one to be 1.1, comma, t. We will do t, 3 of 1.1. This should be on my graph. Ah, okay, wonderful. I love Desmos. Okay, so you see here, this is the point on this third order Taylor polynomial, right? And this is the point on my graph, and how far apart we are. We're trying to get this theoretical upper bound on error. And this is the topic of today's lesson. Okay, so generally, we have a function, f of x, and we want to know how good of an approximation is this TNFXA to this nearby the center. Okay? Well, to do this, we have to discuss error. But before I discuss error, let me define some other things. First of all, we will define the remainder. And all of these little terms have notation that looks like this. The notation is R, N, F, X, A. And all this is you take the function and you subtract the nth order Taylor polynomial. Okay? So you see, if you have a perfect approximation, which you won't, the only way the Taylor polynomial will equal the function, at least for all x, is if the function itself is polynomial. And then if you take the same degree as you do the function, they're equal. We started with that with approximating polynomials. So typically these will not be equal, right? Because most functions we're handed are not polynomials. And so we introduced this term. Now a comment here, before I go any further, is you could also write it this way, that the function itself is, let's just add, it's the Taylor polynomial plus the remainder. And this will come up a little bit in the next video. I'm just going to talk a little bit about the idea of when the Taylor series actually equals the function, and it has to do with this remainder term, but that's for next time. Okay, so this is more a comment, and then the nth order error, this should be little n, the nth order error, this is what we would like to bound. Error, this is the topic of today. All we do is we take, well, here's the notation, and this is the absolute value of the remainder. Okay? So error, first of all, remainder may be positive or negative because you're just, this might be bigger than the function or less than the function. But the remainder, I mean, the error is always non-negative because you're taking the absolute value of something. Okay, well, let's begin discussing error with the simplest possible case. And this is going to tie us to something that we saw in Calc 1. Okay, so let's discuss the remainder term, I should say, or error. One is just the absolute value of the other. Error, absolute value of remainder. But let's discuss this in the case where n equals 0. Consider this, T0fxa. Well, we know what this is, right? The 0th order Taylor polynomial, it's just the function value at a. In fact, we saw this with our approximating polynomials video even, and we've seen it since then. Okay, so let's write the remainder here. The remainder R0 f x a will be the function at x minus the function at a. Let's go back to Calc 1 with mean value theorem. Okay. Well, maybe for the purposes of stating this, I will assume, let's say, x is bigger than a. Although it really doesn't matter, I would just state it differently. Okay, mean value theorem. Who remembers? It says, well, or what I will say about it, as f is differentiable on, let's say x is bigger than a, so this would be a to x, there exists a c in, it says something about the open interval, but I'll put the closed interval. It's fine, because in particular, if you are in the open interval, then you are in the closed interval. So it's fine to state it this way. There's a c in here such that, what does mean value theorem say? It says that this is, okay, it says that if you are on some interval, then there is some c in the interval such that the instantaneous rate of change at x equals c equals the average rate of change over the interval. This is the mean value theorem from Calc 1. And for example, if I multiply through, I get f prime of c times x minus a, well, that this equals f of x minus f of a. This is directly from the mean value theorem. Well, what do you see here? This is the 0th order remainder, and this is the 0th order remainder. So I can just put this here in the light of what we're working on now. So the mean value theorem gives us there is a c between x and a. That's how we would say it if I took off this assumption. We would say between x and a such that, so we get that this 0th remainder, this is directly from mean value theorem, is f prime of c times x minus a. Okay, now what do you notice here? And this is the reason I'm starting with this, because I'm about to state more generally, it's something called Taylor-Lagrange theorem, although you certainly don't have to remember the name per se. We need to know how to use it. But what you see here is that the remainder, right? It looks like the very next term, because if you go to the first term, this wouldn't be a c, it would be f prime of a times x minus a, okay? So it looks like the very next term, except for evaluating the derivative at a, is evaluating at some c. And I will write this for some c between x and a. Okay, this is directly from mean value theorem. Well, I have space. I will state below generally what's true. So now generally, and then we will put this to use. Generally, okay, and I mentioned this is called Taylor-Lagrange theorem. It is more general. It says that the nth remainder, the nth order Taylor remainder. So now this is the difference between the function and the nth order Taylor polynomial centered at a, not just the 0th, right? This is the nth order remainder. Okay, I said that more than once. Well, that this equals, we go, it looks like the next term. Except, instead of, so this is what the next term would be, except evaluated at c. And this is for some c between x and a. Okay? Now, we are not using this to try to find C. In fact, you won't find C, okay? It's not something that is going to be easily solved for, and that's not even our goal. We are using this so we know exactly this is not a less than or equal to. This remainder is exactly this. Well, for some C. But then what we're going to do, because we're interested in error, we're going to put absolute values, and we're going to look on our interval, see how big can this be, and how big can this be, gives us an upper bound on the error. And this is what we want to do. We want the third order Taylor polynomial. At 1. Okay, now. Oops. Now, I will tell you, if maybe I'll write it over here in a box. What did I just erase from the board? Well, it's what the remainder looks like. I will take absolute values and get error. Okay, so what did we have for the remainder term? In this case, it's R3fx1 will be equal to, well, it looks like the very next term, which will be the fourth derivative at some C over 4 factorial x minus 1 to the 4. So this is what we're going to take absolute values of. I hope you can see this red. This is my comment box before I get started. The fourth derivative at C over 4 factorial over x minus 1 to the 4th power. And then you see I'm evaluating my function at 1.1, and so the interval I will use, okay, and I'll get to that when we get to it. But my point in bringing this up now before I even start the problem is the following. You see, it is the next term, except it's not evaluated at 1, but it has that form. So when you start a problem that involves Taylor polynomials and error, whatever order Taylor polynomial you need to calculate, you can save yourself work at the beginning by taking one more derivative because it's going to come up in the error. Okay, so I need to go through k equals 3 to get the third order Taylor polynomial, but then I'm going to take one more derivative because this will come up in the remainder equivalently in the error calculation. But with this one, I'm not evaluating this at 1 because this part is not part of my polynomial. So I will just keep going with my derivatives, take one more. I'll use that when I get to the error part, which if I label these A, B, C, this would be C. Okay, here we go. Well, this is x to the 1/3, 1/3, x to the minus 2/3, then it's minus 2 over 9, x to the minus, let's see, 5 over 3, right? It's all power rule. You just have to be a little bit careful because it's negative exponents and it's fractions. Okay, and then I get 10, positive 10 over 27, x to the negative 8 over 3. One more, this is what will come up in my error calculation. I get 80 over 81, x to the negative 11 over 3. Okay? I'll just leave that there. Now I evaluate at 1. Whew, this is the easy part. 1 to any power is 1, and so I just get these. And finally, I divide everything, or each term I should say, by k factorial. So I get 1, 1/3, 2 factorial is 2. And here I'm going to get, how does this simplify? Well, it'll be maybe I'll write it at first. It's 27 times 6 Yeah, well, yeah, I'll write the 6. 6 is 3 factorial. And then you see I'm going to get the 2's can cancel each. I will get 5 over 81. Okay, so now for my third order Taylor polynomial, maybe I'll put a line right here. T3F, oh, no. I started writing my indices in the wrong place. X1, we see it here, so this is 1 plus 1/3, x minus 1 minus 1/9, x minus 1 squared, and then plus 5 over 81, x minus 1 cubed. Okay? Approximate this. So what do I want here? And this is kind of like the example that I started with. I want, this is part A, okay? Part B, maybe I'll also put B. What I want here is I just evaluate this polynomial at 1.1, 1.1, comma 1, which, let's write it, and then I'm going to have to look and see what I got in my calculator. This is 1 plus 1/3 times 0.1 minus 1/9 times 0.1 squared plus 5 over 81 times 0.1 cubed. Okay, this is the Taylor polynomial approximation of this value. Approximately 1.032284 here. Okay, part C, we want E3Fx1, which is the absolute value of the remainder. And we know the form of the remainder. I'll just recopy. It's the fourth derivative evaluated at C over 4 factorial x minus 1 to the 4. And this is for some C. Well, sometimes you're told the interval. Here we're not told it. We're trying to find the error for a specific calculation. And so as I wrote up there, you go from the center to the value that you're using in your approximation. So my interval goes from 1 to 1. Maybe I should write it above. It might be too low to see. For some Cn, my interval goes from 1 to 1.1, like this. Okay, now I'm going to write, well, see, this is why I calculated the fourth derivative already. So this is, if I fill it in, this is 80 over 81, and then I have C to the 11 over 3. And then I have this part, x minus 1 to the 4th over 4 factorial. And this is times. Okay? So far, this is exact, equals. But this is a very important step, what I'm about to do. And this is something that students struggle with. Okay? What we need to do, you see we have two things that vary across the interval. One of them is this part. It's the fourth derivative. It varies over the interval. One of them is, I'll do it in red, this part. It varies over the interval. Okay? I want to confidently say my error is less than or equal to some number, and have it be less than or equal to, on my whole, 1 to 1.1, which means I'm going to make this quantity outlined in green as big as I possibly can on my interval. And then separately, I'm going to make this quantity outlined in red as big as I possibly can on my interval. Okay, this is why you have to think about your interval. Okay, so how are we going to make this one as big as possible? Well, look at my interval. At 1, it's 0. At the other endpoint, 1.1, that's as big as it's going to be, right? You want to be as far away as possible from your center here to make this as big as possible. And that happens at 1.1, okay? So I will put here, let's recopy. This is important. A, we have calculated 3fx1. This is 1 plus a third, x minus 1, minus a ninth, x minus 1 squared, plus 5 over 81, x minus 1 cubed. And then we have calculated b, that the cube root of 1.1 is approximately 1.0322284. And this value came from our Taylor polynomial. And now we are in C. And I'm going to recopy part of this so that we can, this is equal to absolute value of the fourth derivative at C over 4 factorial x minus 1 to the fourth. And then I will recopy this part, and then I can erase, and we have lots of space to finish the problem, because I don't want to cramp it in down here when this is quite an important part to get down this error calculation. C to the 11 over 3 times, this is already non-negative. Okay, now we have more space, so we have more than enough room to finish the problem. What I was saying, we want to independently make this in green as big as possible on our interval, and in red as big as possible on our interval. The red I'll do first because I started talking about that. The biggest it can be is at 1.1. You go as far away from the center as possible. So I will first keep this the same, and then I will just evaluate this at 1.1, which is 1.1 minus 1 to the fourth over 4 factorial. This will be 0.1 to the fourth, right? Okay, in any case, I'll do that in my next step. So now what I want to do is look at this. This is already a number. I want to look at this and ask myself, how big can that be on my interval? Well, here is where we really have to think about the function, and this will change problem to problem because remember, this was the absolute value of the fourth derivative. So what you want to think about, and I will draw two functions over here to think, well, you'll be given a fourth derivative or n plus first derivative more generally. You won't be given, I should say you will compute, right? Then you take its absolute value, and that absolute value will either be increasing or decreasing. So if you have a decreasing function, it looks something like this. If you have an increasing function, it looks something like this, okay? Now I have a closed interval. Let's say A to B, or A to B. To B, here. Now, if you have a decreasing function, what's the largest it can be? It is at the left endpoint, right? If you have an increasing function, what's the largest it can be? At the right endpoint. So this is what we need to use when we are figuring out what's going on. Okay, so here, if we look at this function, well, the denominator is growing. This is decreasing, so it's going to be like this. So the largest this can be will be at the left endpoint, which is at c equals 1. This is the largest it can be. Okay, so this will be less than or equal to, I evaluate at 1, I get 80 over 81, and then in the denominator I have a 4 factorial, and here I have 0.1 to the 4. Like this. This is the upper bound for error, which, what do I get here? This value is, let's see, approximately 0 point, and then we have 1, 2, 3, 4, 5, 4, 1, 1, 5. And I will say, this is a theoretical bound. Okay, it's a theoretical bound. We computed it, well, using this theorem about the fact that the remainder, that there exists this C, right? So that this is the remainder, and then we looked at how big can this be, how big can this be. It's a theoretical bound. But we could also, and I have this just out of curiosity, if I take this out a few more decimal places, this has a 395, okay? And then, because we do have fancy calculators that can compute the cube root of a number, we can look at this, for example, the actual cube root. Well, again, it's rounded. I have 1.0322811, okay? So we can compute the actual error on this specific approximation, right? Just by taking the difference, and just out of curiosity, we can compare the two. It should be a number less than this theoretical bound. I have 0.12345, and then I have 384. Okay? So you see, in fact, we have 5 zeros followed by a 38, 5 zeros followed by a 4-1. I'm less than the theoretical bound, as I'm guaranteed to be, but it's a pretty good theoretical bound because it doesn't differ from the actual error all that much. Here's another example, and this will be a part A and a part B, and this one we're going to have to think a little bit. Well, I'll get to it when we get there. This came off an old final exam, and it's a great practice of everything. So what do we need? Third order Mclaren polynomial. This is the start, so we are centered at 0, and then what's different here is we don't have a specific approximation we're trying to do. In the last one, we were trying to find the error for a very specific calculation, which was the cube root of 1.1. Here, I'm trying to find the upper bound for the error sort of for any approximation I did, as long as the absolute value of x is less than or equal to 0.15, and we will get to that. But part 1, or part A, I should say, is a Mclaren polynomial. We take the kth derivative. We take the kth derivative at 0, and finally the kth derivative at 0 over k factorial. Okay, I'm doing third order, but I look ahead and I see I need error, and so I will go ahead and take that fourth derivative, but then not fill in this part, not fill in this part for k equals 4. Okay, and this is an exponential. It's when we differentiate, it's technically chain rule, but the inside function has derivative -2. My original function is here, and then I have -2e to the -2x. We have +4 e to the -2x. We have -8 e to the -2x. And finally, it's going to be 16 e to the -2x. Then we evaluate at 0, and e to the 0 is 1, and so I'm just copying down these coefficients here. I don't need it for the fourth. This is just for my error. Finally, I divide by k factorial. So this is 1 minus 2, and then 4 over 2. Maybe I'll write it, which is 2. And then minus 8 over 6, which is -4/3. Okay, so part A, my Taylor polynomial, we have this t, part A, t3fx 0, okay? Or Mclaren polynomial, I should say. It is a Taylor polynomial with center 0. This is 1 minus 2x plus 2x squared minus 4/3 x cubed. Okay, so this is part A. Now let's get into part B, which is the error calculation. Okay, so I have the following. I know that the error will be equal to absolute value. Okay, well, it's going to be the fourth derivative at some c over 4 factorial. Well, I don't have an x minus a, it's just x to the fourth. My center is 0, right? Makes it a little bit easier. Now I need to think about my interval because it's not an error calculation or upper bound for just one approximations. It's anytime absolute value x is less than 0.15. So this, my interval I will use is, well, it's 0.85. No, I don't know what I was doing. Negative, I was thinking x minus 1 and absolute value less than 0.15. It's just absolute value of x. So this goes negative 0.15 to 0.15. Okay, this is my interval. Well, my fourth derivative is 16e to the minus 2x, right? And this is always positive. So this would be 16e to the minus 2c over 4 factorial. Okay, and then I have a fourth power, x to the fourth, which is always non-negative. So again, just like in the last one when I had a fourth power, I don't have to worry about absolute values. Or I could leave them, but it doesn't really change anything. So this would be times x to the fourth. And then, just like in the last example, in fact, I will box them in, what we'd like to do is make this as big as possible and also make this as big as possible. Or I could have put the 4 factorial underneath the x to the fourth. Okay, it's just a constant, in fact. But it's this part and this part with the c and with the x, I want to make as big as possible, sort of independently on this interval from minus 0.15 to 0.15. So let's think about the exponential function. I do not want to leave e to a power in my error bound, because if you think about it, look, I am approximating e to a power. If I'm approximating e to a power, well, I don't want to say that my error is less than or equal to some number that has e to a power in it. That's kind of circular in the reasoning. And if I was legitimately approximating e to a power, knowing that my error in that approximation was less than e to a power, it would really tell me that much information. Okay, so what could we use about e? And this will come up in, not the next example, but the last example I will do, which is in 2 examples after this. We may use that 2 is less than e is less than 3. In fact, you can prove this with series. Remember how I told you this? You can take that as a definition of e, and using this, you can prove it is between 2 and 3. I think I have that in one of my videos. It's a proof that's a little bit advanced for 1342. This is Calc 2. But it's the proof that e is irrational. It uses series and it uses a proof technique called proof by contradiction. But we can, okay, I proved it using just this definition, and it has ideas of Taylor polynomials and remainders and things like this. It's actually a really cool proof. But anyways, we may use that 2 is less than e is less than 3, okay? And what do we know about the graph of, well, any kind of exponential with base bigger than 1, it looks like this. And, well, let's say 2 to the x would be here. And then 3 to the x would be here. 3 to the x. Of course, it's not very accurate on this side because they are decreasing. Okay. And then in between, because e is between 2 and 3, y is e to the x, and black will sit between these two. Okay, so you can take this as just known, okay, but we can't use a specific value. If you have to get e by typing it in your calculator, you don't want to leave it like that. That's the whole point of this. We're approximating e to a power, so you don't want to use the e to the button in your calculator in this upper bound for the error. Okay, now I will continue to work in my side box for a moment because let's not worry about the coefficients. Let's just, or maybe I'll just look at the numerator, which really is the fourth derivative. Okay, so my fourth derivative at c, forget my parentheses, is 16e to the minus 2c. Well, if y is e to the x is increasing, this function will be decreasing, okay? Decreasing because it's a 1 over an increasing function. And then, so this is going to be the biggest at the left endpoint as we discussed in our last example. This is less than or equal to 16e to the minus 2 times minus 0.15, which is 16e to the 0.3. Okay, this is where I was saying you don't want to just write less than or equal to and replace this with the 16e to the 0.3. This would be the circular reasoning. So how can I get a handle on e to the 0.3, excuse me? I just need, I will underline, I just need a reasonable upper bound. Okay, well, let me now, maybe I will erase over here. And make an observation. In this box, e to the 0.3 is definitely less than e to the 1/3. Why is that? Well, I just erased it, but it's an increasing function, which means if I replace with a larger value of x, 1/3 is bigger than 0.3, then, well, e to that is larger than e to the 0.3, for example. Now, looking at this, this is less than this, okay? And then I can say that e to the 1/3 is less than 2. Now, this is a question you might ask yourself. So question, why is e to the 1/3 strictly less than 2? Well, how do we see this? It's less than 2 because, well, e is less than 2 cubed. Right? This is 8. And I've just said that e is less than 3. Without a doubt, e is less than 8. Okay, so e to the 1/3 is less than 2 because e is less than 8. Okay, well now I have, you see through this two-step process, I have a reasonable upper bound on e to the 0.3. I can say it's less than 2. So now let's come back here. This would be, well, we know strictly less than, although you can say less than or equal to. This will be 16 over 4 factorial times 2. Okay, because that's e to the 0.3. And now, what's the biggest x to the 4th can be? Well, you want to be, it's really either endpoint here. You want to be as far away from the center as possible. So this would be 0.15 to the 4. And then, let's see what this is. This has 0.123 675. So this is, we have three, after the decimal, we have 3 zeros followed by a 675. This is my theoretical upper bound for error, reasonable upper bound for error. Anytime I use this third order Taylor polynomial, Mclaren polynomial, to approximate the function when the absolute value of x is less than or equal to 0.15. Let's do one more example of this type, and then I'll do something a little bit different. In this one, we have the cosine. This one will be actually easier than the last one we did. We want to find the fourth order Mclaren polynomial, and then find a reasonable upper bound on error. And again, it's going to be over some interval. So in particular, I can write immediately, maybe I'll write it at the top, that my interval is minus 0.2 to 0.2, okay? So this is the interval I will use when I'm doing my error calculation, or upper bound on error, I should say. But we start with the fourth order Mclaren polynomial. Here. Okay, switched blues. Hopefully this is darker. I need fourth order, but it's error, so I'm going to take one more derivative, and this fifth I do not need to evaluate, and then I do not need this one. The fifth derivative will just come up in my error calculation. Okay, so we start with the cosine and we start differentiating. This is very much like we did the sine in the last video. So we take the derivative. We take the derivative. We take the derivative, positive sine, and then one more cosine. Okay. Oh no, I lied. Now one more, because for error, right? We need one more now. Negative sine x. Okay, great. Now we're okay, right? This should go cosine minus cosine, sine, cosine minus sine, like this. It would keep spiraling through this forever. In particular, we were talking about this a little bit at the last video with our Mclaren series, and we will do more of that again. Right now, of course, our focus is polynomials and the error. Okay, then we evaluate at 0. Okay, not for this one. And then we divide by k factorial. So we have 1, 0, negative a half, 0, and then 4 factorial is 24. So this is a positive 1 over 24. Okay, now I can write out my Mclaren polynomial. This is T for f x 0. But there's only 3 terms because I have these zeros here. I have 1 minus a half. This would be x squared. And then plus a 4, oh no, 1 over 24. I almost said 1/4. 1 over 24 x to the 4th. Okay, this is part A. That wasn't too bad. Well, I don't have them listed A and B, but we have found A. Now we need this error. And again, this one won't be too bad either. E4 f x 0 will be, by this Taylor-Lagrange theorem, its absolute value. We take the very next one. So this would be the 5th derivative, evaluated at some c over 5 factorial x to the 5. Okay, you look at the very next term, it looks exactly like, well, a term here, except here this is not 0, it's some c, and we can't solve for the c, and that's not our goal anyways. Okay, well, you see we have the 5th derivative. It's negative sine Well, this is a very nice one to work with. It doesn't matter if it was the 10th derivative or 152nd derivative here for the cosine, or if I had sine, because I am going from between plus or minus cosine, plus or minus sine, and these are all live between -1 and 1. Okay, so here immediately I can write this is less than or equal to, just put a 1 here. That's the biggest it can be in absolute value because it is either sine or cosine. We know it's negative sine, but the biggest negative sign can be in absolute value anywhere is +1. Okay, so this is just absolute value x to the 5th over 5 factorial. And now, well, now I need to actually look at my interval, which is here. Okay, how big can absolute value x to the 5th be as far away from the center as possible, which would be 0.2 to the 5th over 5 factorial. This is approximately, let's see, let me count them, 1, 2, 3, 4, 5. There's a point, 1, 2, 3, 4, 5. And then it's 2, 6, 6, 7. Okay, well that's rounding to 4 decimal places past the leading zeros. So this is the upper bound on error anytime you use this polynomial. This is the 4th order polynomial to approximate the cosine on this interval, -0.2 to 0.2. The nice thing is, right, and this is one that actually makes sense to us. Sometimes 1 over something, you think, well, I could do that, not too hard. But let's imagine the cosine. I only know the cosine at a few numbers. I know 0, pi over 3, pi over 6, pi over 4, pi over 2. Really, that's it. Everything else I get by drawing a unit circle and using a reference angle. How many numbers in here do you know the cosine for? 0 off the top of my head? Well, that's about it, right? Pi over 6 is going to be bigger than 0.2, for instance, because pi is about 3, more than 3. Yeah, so I don't know any other values in this interval for the cosine. But you see, I can get within this of the cosine just by evaluating this polynomial at any value in here. And this is the beauty of the Taylor polynomials. I can get the cosine very, very close for some values that there's no way I would learn them off or get them off a unit circle, for example, just by evaluating this polynomial. Okay, now let's do one more that's a little bit different. It is more like trial and error type, but it's a nice thing to think about, and it uses error and remainder like this. Let's approximate E to within an error of at most 0.001. Okay, now this doesn't sound like what we were just doing, but it's super cool, and we can use these ideas from this section. So we can use here, and I will, this Taylor polynomial, which is the sum, k equals 0 to n, of x to the k over k factorial. This is the nth order Taylor polynomial for f of x. This is for f of x is e to the x. This is the Mclaren polynomial. We see the center is 0. In fact, we know, and we discussed this in the last video, if we go to infinity, just put an infinity here, it's something called the Mclaren Series. And this is the nth order partial sum of that series, okay? But I'm going to use this, okay? Now, what I will do is, okay, so I am going to use this. We will use T, N, F, X 0 to approximate e to the x. Well, what's the only approximation that I need, right? Well, let me change this slightly. I want to approximate e, so I'm using TF here to approximate e here, right? So I'm using this at 1, which means, and this goes back to the very first example, except it's still a little different. I have a very specific approximation I'm trying to do, right? It's this function at 1. Okay, so this will say, I'm going to use the interval. The interval in my error calculation is, well, you go from the center to what it is you are approximating, which is the function evaluated at 1. Okay, well, you see the problem is I have an upper bound on my error already. This is different. Well, I don't know if it's a problem, but it's different. I have an upper bound on my error, and I want to find n, well, the smallest such. Maybe I'll write that, the smallest n such that this error, e n f x 0, is that I can prove that the error is less than or equal to 0.001. And then, well, I can just evaluate that particular Tn, whatever this n is, at 1, and I will have an approximation of e. That's within this. That's the whole idea of this error thing, right? But unlike the examples that I've been doing, I'm given an error, and I want to be less than or equal to that error. And I know my interval, but I want to find the capital N, smallest such, that will work. Okay, so let's do it. Well, I know this one is nice because I know what the derivatives are. All of the derivatives forever for e to the x are e to the x, right? So now let's begin. Maybe I will start in blue. This e n f x 0 equals, well, absolute value, it's the n plus first. Maybe I will write it at c over n plus 1 factorial times x to the n plus 1. Okay, and this is for some c on my interval. I already discussed this was the interval for this approximation. We go from the center to the value, it's here, 1, that I'm using. Well, as I mentioned, or you can calculate, the n plus first derivative is e to the x. And so well, everything here is positive because I'm only feeding in non-negative numbers, or I should say non-negative. This will be non-negative. This is e to the x. This is positive. I can drop my absolute values. Okay, so this will be equal to, this is e to the c over n plus 1 factorial. And then I will just go ahead and put this for the moment, x to the n plus 1, okay? Then just like in all of the problems we do with error, we have two things. We have this, we want to find an upper bound, and we have this, we want to find an upper bound independently over the interval 0 to 1. Well, what can we use here? Okay, maybe I will try to do a side box over here. Let's think about e to the c. Okay, first of all, we've already discussed 2 examples ago, e to the x is an increasing function. Okay, so the biggest it's going to be is going to be here. So we know e to the c is less than or equal to e to the 1. Well, this might make you think about why the circular reasoning is an important thing to have, or to not have, I should say, to pay attention to, because I'm trying to get e to within an error of 0, 0, 1, or find the n, right? And here, I can't have e in my error. That wouldn't make a lot of sense. But what do we know, right? I mentioned we can prove using series even without a calculator. E is between 2 and 3. And so this e is without a doubt strictly less than 3. So this is what we can use here for my first less than or equal to. So this will be less than or equal to 3 over n plus 1 times x to the n plus 1. Now how big on the interval 0 to 1 can x to the n plus, oh, factorial, factorial, factorial. No, it's okay. How big can this be? Well, it's the biggest when you're as far away from the center as you can be on your interval, which is at 1 to the n plus 1. 1 to the n plus 1 is 1. So this part, now I can replace with another less than or equal to. It's just here. Okay? Great. Now let's go back to what we're trying to do. I want to find find n, so that this is less than here. Okay? So I need to, I'll write this down below, find n such that 3 over n plus 1 factorial is less than, well, this. But let's think about this, because I'm going to try and rewrite this. This is 1 over 1,000, right? So let me just change it now. This is 1 over 1,000. Well, this will happen. Let's see. If I I'm trying to, I don't want to just cross multiply because it's not equal, it's strictly less than. So if I change this to match the numerators, then I will have a better, I can put a 3, I can put a 3. And this fraction here is literally equal to this, right? It's 1 over 1,000, which is this, right? But now I can go back to my observation. This fraction and this fraction have the same numerator. If I want this less than, it says the denominator must be greater than, right? I have lined this up to help myself. So I need n plus 1 factorial bigger than 3,000. So, or equivalently, I need n plus 1 factorial bigger than 3,000. And now I'll say try sum n. Okay? You kind of want to jump up and not just start with 2 factorial, for example, or 3 factorial, because you know those are less than 3,000. So let me show you some calculations. 5 factorial is 120. 6 factorial is 720. 7 factorial is 5040. Okay, this is the first one that's bigger than 3,000, which says you would take n plus 1 to be 7, or n equals 6. Okay, now this says this is the Taylor polynomial we want to use to approximate e to within point. It's erased. We use, I'll write it, T6F, let's see, 1, 0 to approximate e to within, well, it was 1 over 1,000, like this. Okay, and we will do it just to finish the problem. We will get an approximation of e that is within this, but my approximation comes from the Taylor polynomial. It does not come, I have never at all today typed E into my calculator, for example. Okay, so this 1, 0, this will be 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial. Now this part I will type in my calculator. This is approximately 2.718056. Okay, now this part is taking it a little too far. We wanted it within 0, 0, 1.